which tells us when it came out, we know what it is. It comes out in 40 minutes, we know it's C. So, I mean, for example, let's say this is heroin, and this is fentanyl, and this is, codeine. So we see this chromatogram, we see, well, that peak comes out right when heroin comes out, so we know there's a lot of heroin. This peak comes out when fentanyl comes out. Oh, that must be fentanyl. Not much fentanyl in there. We see someone go in 2 hours. That's codeine, because after all, it's coming out in 2 hours, and codeine, we know, comes out in 2 hours. So by looking at the chromatogram, we can also find out pretty much what is in there. Now, it's not perfect because sometimes things come out at more or less the same time as others. So it's not only, let's say, heroin that comes out in 40 minutes. There may be other things that come out in 40 minutes, but it's a good initial idea of what is coming out. This chromatogram can give an idea of what's coming out. It's not perfect, but it gives a good idea. We do need some other information as well to make a positive identification of what this band is. Now, remember, we're detecting it with a detector, right? We are using a detector. This detector can sometimes not only detect that something is coming out, as whatever comes out, it gives a peak. It can also detect, especially if it's coupled with or it's a specific kind of detector, it can detect what is coming out. It can not only get a signal of something is coming out, it can give a signal of what exactly that is that's coming out. And we need specific detectors for this. So let's talk a little bit about the detectors. We'll talk about columns first. Remember, the columns are used, they separate between these components. And as I said, there are different kinds of packing of the columns. There's different kinds of liquid eluents that flow through it. And believe it or not, also pumps that pump at different speeds, but we're not going to deal with that. Also different kinds of detectors, but we'll talk about the detectors after we talk about the difference of columns. So, as mentioned, the column is packed with something, and the different components stick to it in different ways. Now, some of them are based on the solubility in the eluent that you put in. The more soluble it is, the faster it'll go through. So that is one way of differentiating between the different components of the solution. Some are more soluble than others. The more soluble ones will flow through faster. Some are based on the polarity of the molecules. Well, if it's more polar, it'll stick to the let's say the powder that packs it. Less polar will not stick. Or just the opposite. You might have something that the more polar, you can go either way. The more polar, the more it'll stick. The more polar, less it'll stick. It depends on the packing. So again, different columns deliberately differentiate between how soluble something is, or they deliberately differentiate between how polar the molecules are. Some of them based on the charge. If the molecule isn't just polar, as like more of a positive charge and more of a negative charge on one side, it has an actual positive charge and sometimes a 2+ charge or 3+. Well, sometimes it separates based on that. Something has a 2+ as opposed to 1+, it'll separate that. One will flow through the column faster than the other, and you can separate it that way. Some are based on molecular sizes, that the larger size will flow through slower. You can develop columns, and we have many different columns, and some columns are deliberately designed to separate them based on molecular size. So we have a lot of versatility. This is a science that has been in great development, and we have many different kinds to suit pretty much any one of our needs of separation. Some of them, these often separate faster and more clearly. They use gas instead of a liquid. This is a very interesting idea. A gas flows through. It's not a liquid. We take, let's say, argon, some inert gas, and we have this gas flow through. And your sample has to be a gas, so you have to heat up your sample, and not so enough to burn it or destroy it or react it with anything, which is always a problem. You heat something up, there may be some reactions. Anyway, so you heat it up, especially if it's volatile, if it evaporates easily, heat it up, it's a gas. You have that gas be pushed through a column, and some of the gases, some of the components of the gas will stick to the column. Now there might not be sand inside it that the gas sticks to. It might actually be just a coating on the inner edges of this column. That some gases, again, they're all they're all evaporated. Some of these evaporated gases stick to the liquid on the side, or the fluid or whatever is on the side, and they hang back, like this one, let's say. It would hang back. Some of them slip right through. That's like this. That's this one. Generally speaking, if a gas is what's pushing it through the column, and all these things are gases, you need a long, long column, which is not a big deal. They have a lot of these long columns. They coil them all the way up. They coil them up so they don't take so much space, but they separate very well. This is what they call gas chromatography. In short, it's called GC, for gas chromatography. So we start off talking about liquids that flush it through, but again, you can have a gas that blows it through. And if everything's a gas and a gas blows it through, some gas will cling to the sides or whatever you pack the column with more than others, and you can separate different gases that way. They separate very well. The problem? Not everything turns into a gas very easily. Now, in cases of arson, for example, where we're looking for gasoline or kerosene or something that started the fire, made it burn hotter or made it burn more easily, these are very volatile. I mean, we know gasoline and kerosene, they're very volatile. So these are very easy. You heat them up, they'll all turn to gas, blow it through this column, maybe a long column. Kerosene will stick in one, will, let's say, hang back more, depending on what's going on with there. And let's say gasoline will go a lot faster. So you can separate the different components of whatever was heated and turn it into a gas. You can separate with a gas chromatogram, or a gas with gas chromatography. Okay, so there's liquid chromatography. We use a liquid to flush it through. There's gas chromatography, which uses a gas to flow it through. But it's all the same idea. Some things cling to the column more; they hang back. Some things just slip right through; they go forward. They all cling differently. They all go through at different speeds. They're all detected at different times, and they give you this chromatogram. And this chromatogram will tell you what was in general. Will tell you what was in there. It's not that good because some things do have the same what they call retention time, meaning the time it sticks back in the column. So we'll have the same. So it's not that good, but it does give you an idea of what is in there. To find out and make sure exactly what it is, you'd have to make sure to identify each column. Like you might have to once it's separated, you don't have to worry about something else interfering because it's all separate from everything else. But you would, let's say, collect this part and analyze this part separately to know exactly what it is. Anyway, so that is some of them use a flow of gas instead of a liquid. Okay, we mentioned that the liquid is on the side. Same idea, that it sticks more, therefore it hangs back more, therefore it's separated from the others. Sometimes there is something called TLC. It's thin layer chromatography. This uses a solid plate. It's we're not going to go into it too much. The idea is, let's say you have this. They have these things. Let's say paper. It's usually not paper. It's usually